AP Chem. I just have a short little note section about titrations, since I'm not really sure if it would be fair game for the AP test or not, because technically they're covered in Unit 8, but there's also some acid-base stuff in Units 4 and 7, so I just want to make sure we get a little information about titrations, plus you'll probably encounter it when you do chemistry in college, so it's good to know about it. So our setup for titration is pretty simple, actually. The most important thing that you've probably seen before is the burette. Okay, so this is mentioned in the Thou Shalt Not Forget notes about how to read a burette, but it's a very accurate instrument for measuring the volume of a substance. And it's kind of like the opposite of a graduated cylinder, where if you have a graduated cylinder, it goes like 1 milliliter, 5, 10, 15, 20. This one goes lowest on top and then works its way up to the bottom. So you kind of read it from top to bottom rather than bottom to top like you would for a graduated cylinder. And that's because you are usually adding to some solution down here. And so the volume changes this way so that the more you lose, the more you're adding to the solution. So that's why the numbering system is kind of like backwards. Then there is like this little valve that they call a stopcock. So you twist it to add titrant to the analyte. And depending on how much you twist it, depends on how strong your stream is, basically. So usually you try to do it dropwise, because the slower you go, the more accurate you're going to get to reach what's called the end point or the equivalence point of the reaction. So this little valve is very important. You should always remember which way to turn it, because the quickest way to ruin your titration experiment is to turn it the wrong way, going past your equivalence point and ruining pretty much all your data, which will happen. It's annoying. And then at the bottom, you have a flask that contains your analyte, what you're analyzing. So the burette has the titrant, what's being added, and then the flask contains the analyte, what you want to analyze. Usually you add like a stir bar at the bottom. That's just a magnetic stir bar that you can turn on. Usually it's a setting on a hot plate. You don't have to have the hot plate on, but you can stir the solution. That helps to mix everything nice and easy. And also, sometimes this flask will also contain some sort of indicator, whether it's an acid-base indicator or something that indicates when your end point has been achieved or reached. So this is kind of how you read a burette. So the smaller numbers are on top. So this is the very top of the burette at 0 mils. And then you fill the burette with your titrant, what you are adding to the solution in the flask. So you can fill it up. You don't have to go to 0 milliliters. You can go pretty much anywhere. So this person, they filled it to, would be 0.5, so 0.6, 0.7, I would say 0.72 milliliters, okay? So when you read any instrument, remember, you go to read as many lines as you can, and then you estimate 1. So I can read to 0.5, 0.6, 0.7, and then I'm estimating that hundreds place of the digit. So I'm going to say 0.72. You might say 0.71, just depends on how you read it or interpret it. Then I add my titrant to the flask. The indicator shows me that I have reached an end point, so I'm going to read the final reading in my burette. Okay, so there's more to the burette up here. They've just cut it off to make the picture more legible. But here I'm going to read 49.5. Okay, so this is 49.5, so this would be 0.4, 0.3. So I would read 49.3 and then estimate. That's pretty close to 0.4, so I'm going to say 49.38 milliliters. Okay, but again, that last digit is estimated, so you could say 0.39, 0.37. That last digit is the estimated digit, which we always estimate 1 digit for significant figures. So that's how you read a burette. It's kind of different than how you would read a graduated cylinder going from bottom to top. So the definition of like what a titration is, it's just a laboratory method that we use to determine the concentration or the pH of a substance with a known composition. So we know the chemical formula of the substance, the analyte, but we don't necessarily know its concentration or maybe its pH. Then we have a solution called a titrant, which we know pretty much all the information about it that we can. We know its pH, we know its concentration, so we know everything we can about the titrant usually, and we're using that information to figure out more information about the analyte, what we are analyzing. And then we also need to understand the molar ratios of how our titrant and analyte are going to react. So in AP chemistry and most chemistry courses, usually we're talking about acid-base titration, although I will talk about other types of titration. So this has a weak acid and a base OH, could be NaOH or whatever, reacting. So since these react in a 1-to-1 molar ratio, we know that there's going to be, for every 1 mole of OH that we add, we are using 1 mole of acid. That's not always the case. Sometimes it's going to be a 2-to-1 ratio, and that's going to change our math of how it's reacting. So that's why it's important to understand the molar ratios, the balanced chemical equation of what's going on. So acid-base titration is usually the most common that you will see in chemistry courses. So that's when we use an acid and a base. You can determine the pH of the solution. You can determine the concentration of the acid or base with the titration data and the balanced chemical equation. You can also do a titration with redox reactions. Same idea. Usually that's used to determine like the purity of a substance. And you can also do it with a precipitation reaction, where the endpoint is where a precipitate starts to form, and that's also used to determine the concentration of a reactant like acid bases. Important terms are endpoint and equivalence point. So at the endpoint, the indicator, which again is usually in the analyte, changes color to signal the arrival of the endpoint. When the correct indicator is used, the endpoint is very close to the equivalence point, and usually in lab, we say that those two are at the same thing, that they're the same point. So the equivalence point is when the number of moles of titrant equal the number of moles of analyte that were originally present. So that's when the moles of analyte and titrant are equivalent. So that's why it's called the equivalence point. And we want the equivalence point and endpoint to be as close together as possible. So here we have an example of a problem you might see regards to titration. So if we have 30 mils of a 0.5 molar HCl solution that's titrated with NaOH, so we have 0.5 molar NaOH, so we have NaOH in the burette, and we have HCl in the flask with as our analyte. Assume the volumes are additive, and the final temperature of all solutions is 25 Celsius. Now this problem is relatively easy, and I say that because these two have the same molar concentrations. So that's going to simplify things a lot. It's also relatively easy because our H plus and OH minus are present in a 1-to-1 ratio. So it's not that we are reacting 2 H's with every 1 OH or anything like that. So that is nice as well. So we have the initial concentrations of everything. What we want to find is the pH in this problem. So we want to find the initial pH of the 0.5 molar HCl. We want to find the pH after 15 mils of our base was added, after 30 mils of the base was added, and after 45 mils of the base was added. So pH is a measure of the concentration of H plus ions that are in the solution. So in order to determine pH for all these, we would have to know the concentration of H plus. If we can't determine the concentration of the H plus, we could also use the concentration of the OH minus to find the POH, which is just like pH except for in reference to the OH minus. And then to find pH from POH, you know how the pH scale goes from 0 to 14? To find the pH from the POH, you would take 14 minus the POH, and that will give you the pH. Same thing if you want to do the opposite to find the pOH, but usually we reference things in terms of pH. Okay, so the important thing to know here for this reaction is the net ionic equation, what's actually reacting in the solution. It's going to be those H plus ions and the OH minus, and they're going to be forming water, which has a neutral pH of 7. So HCl is a strong acid, so it experiences 100% ionization. That means for every mole of HCl that we have, we're going to get a mole of H plus ions. So with this, since our concentration of HCl is 0.5 molar, that means that we are going to get 0.5 molar H plus ions in the solution. So pH is going to be the negative log of that concentration of H plus. Since, again, it experiences 100% ionization, we're going to have 0.5 moles of H plus ions. So pH is going to be the negative log of 0.5. So our pH of our starting solution is 0.3. So this is a very acidic solution of what we're starting with for our analyte. Part B, we want to find the pH of the solution after 15 mils of titrant was added. So our first step is to find the moles of H plus and the moles of OH minus that react, okay? Because the reaction between H plus and OH minus is going to change the pH of the solution. So first I want to find the initial moles of HCl in the solution, because again it's a 1-to-1 ratio between moles of HCl and moles of H plus. So to do that, I take my volume, which is 30 milliliters, times the concentration, 0.5 over 1 liter, and I find out that I have 0.015 moles of HCl. Then I'm going to see how many moles of NaOH, or OH minus, which is what I'm interested in, was added to the solution. So I'm going to do the same thing, basically. Take my volume, 0.015 liters, times the concentration, 0.5, and we get 0.0075 moles of NaOH, or 0.0075 moles of OH minus, which is what we're interested in. So now we have the moles of our two reactants. Next, we're going to set up an ice table to see our initial, the change, and the final when we reach equilibrium with these two reactants. So my initial, again, is going to be 0.015 and 0.0075. Water is liquid, it's not involved in the reaction, so we're just going to ignore it, okay? Or it's involved in the reaction, but it's not involved with the equilibrium expression, I should say. For our change, basically we're going to use up whatever is present in the smallest amount. So since 0.0075 moles is smaller than 0.015, I know I'm going to react all of this and have remaining H plus in the end. So my change for both of these is going to be minus 0.0075 moles. When I do the math, when we reach the equilibrium of these two reactants, I'm going to have 0 moles of OH left. All of it is present in the water now. And I will have 0.0075 moles of H plus left. So now I have the moles of H plus. Remember, to find the pH, I have to find the concentration of H plus. So I can take these moles and divide by my volume to find the concentration. So my new volume is going to be, they said the solutions were additive, the volumes were. So we have 0.03 plus 0.015. So that tells me that I have a new volume of 0.045 liters. I take the 0.0075 moles that remain of H plus, divide by 0.045, and I find out I have a 0.17 molar concentration of H plus at the end of this reaction. So now I can calculate the pH, which is the negative log of the concentration of H. So my pH is 0.77. Still very acidic. I have not yet reached my equivalence point or anything like that. I'm still very much acidic.